All right, so I'm breaking this up into components because I need to figure out, because force and mass are directly related, that force is equal to mass times acceleration. So this one I don't need to break up because it's already pointing towards the axis. It's already tangent to the path. Try that one again, perpendicular to the path. It's already in the j-hat direction. Weight, on the other hand, part of it's in the i-hat direction, part of it's in the negative j-hat direction, so I have to break weight up. So I have to figure out how much of that weight is actually in the tangential direction. And I'll call this weight T for tangential. And about in that direction is weight sub C for, technically it's pointing away from the center, so it would be a centrifugal or centrifugal component. But
isn't centrifugal like imaginary? It's just like a hypothetical thing?
if you're dealing with a rotating reference frame, that's when it generally shows up. Some textbooks will call it a fake force or a false force. If you go by literally the meaning of centrifugal or centrifugal, that it means pointing away from center. And so, because this is pointing away from the center, that's why I made reference to its centrifugal.
Mm-hmm.
The combination of these two would be a centripetal force because the net force is pointing towards the center.
So it's just like, it's used for calculations because it's easier to use? Because you can.
There are times.
You can just make that just a straight line, like a full straight line.
It depends on what you meant by simpler in the calculations. There are times in which it is convenient to talk about centrifugal force, just like Coriolis force is another force that is not really a real force. But if you're in a rotating reference frame like you're on the Earth, it is sometimes convenient just to use. So anyway, I've defined this angle theta right here, or right here. One of these angles is theta, and one of them is the complement. Which one is theta?
WC.
That one's theta?
Yes,
Why do you say that?
because it is on the opposite side of it. That thing. Oh my God.
All right, when I got two lines that intersect like that, then, yep, the one's on the opposite side. So that would be theta. Therefore, this side right here, would that be involved with sine or cosine? This is my weight here. Sine or cosine?
Cosine.
And why?
Because it's opposite of the side you're trying to find is opposite of the angle. Might be backwards.
Right, so this side right here, so you started out fine, it is cosine, but then your reasoning threw me. So looking at this right triangle here, that's a right triangle.
Yeah.
And I was asking about this side right here.
Yeah.
And you said it's opposite what?
Opposite of the angle.
With this angle right here?
Yes.
Yes.
No.
So it's actually adjacent. So when talking about opposite and adjacent, I've had students in the past who sort of have a picture in their head that's a little bit different than the way the math people think. And I don't know what.
I think I got my SOHCAHTOA backwards.
Ah.
Yeah, cosine's adjacent over hypotenuse, so it's got it backwards.
For those who are not sure, then if this is the angle right here that we're talking about, imagine you're in a room with three sides. The adjacent side, if I'm in this corner, I can touch two sides. I can touch the long one, the hypotenuse, or the other short one, the one that's shorter. That would be adjacent. Opposite's the one that you're facing, and the long one's hypotenuse. So cosine adjacent over hypotenuse. So this one is the cosine, so this would be the weight times the cosine of theta, and so this has to be the other one, the weight times the sine of theta. So we end up with two equations of motion here. All right, so when I say equations of motion, I'm not talking about, Vf equals Vi plus At, or Vf squared equals Vi squared plus 2As. I'm hoping you're familiar enough with those equations that at least that rings some sort of bell. When you first start doing the motion chapters, which is usually chapter 2 in most textbooks, and it's been a while since I've taught the 131, I can't remember where it shows up in this textbook. Chapter 5 in this textbook. I'm not talking about those equations. Equations of motion are all based on F equals ma. So my two equations, I'm going to have an equation, a j hat equation, and an I hat equation. So my j hat equation, I look at all the forces in the positive direction, which is my tension, minus all the forces in the negative direction, which is my WC here, or W cosine theta. It's going to be equal to mass times my centripetal acceleration. In the I hat direction, I have only one force. So I have W sine theta is equal to mass times the acceleration in that direction, which I'll label as A sub t for tangential acceleration. And then I have to make one change. This is the thing that I usually forget when I do this, but I thought about it early this time. So before I throw in, I'm gonna introduce a negative sign in here. Are there any questions at the moment about?
Is that an equal sign? Yeah.
That is an equal sign.
I mean, on the FT?
That?
Yeah.
That's a minus sign.
Okay.
Because I have two forces in the j hat direction, so I'm adding or subtracting. Other questions? All right, so this side over here, these are my forces, and this is mass times acceleration. Now look at the way I've defined theta. I define theta from the vertical. If that angle is 30 degrees, what is theta? It was not a real trick question, it was.
Is what? 30 degrees.
Yeah, okay, so if that's 30 degrees, and typically, yeah. But by making it 30 degrees, you've established that's a positive angle. Negative angles will be over here, positive angles will be over here.
I think you misheard me. I was asking what was 30 degrees?
Oh, that angle.
Okay.
Sorry about that. I was giving you credit for having answered the question. I take it back. So if that is a 30-degree angle, theta is equal to 30 degrees, typically, when I pull it back, making that the positive angle, no problem at all. Sine of 30 degrees is 1/2. It is positive 1/2. If I'm over here at a 30-degree angle, well, technically it'd be negative 30 degrees from a math point of view. So I need to somehow take the angle into account, because this force right here is pointing in that direction. It's pointing opposite of what I said was positive theta direction. I basically have two different coordinate systems going on here. So I introduced this negative sign just to account for the fact that my acceleration is pointing in the negative angle direction. As I say it, it sounds awkward, but the negative sign needs to be there. So the question is, do I have Hooke's law here? Do I have some form of Hooke's law? Well, flashback, Hooke's law, we have negative k delta x is equal to mass times acceleration. That was the original Hooke's law, mass on spring. Then we had the negative g mass 1 mass 2 over r squared. Over big R cubed, little r is equal to mass times acceleration. I guess at this point we're ignoring the vector piece of it by putting negatives in here. We have some sort of acceleration here directly related to a position, except with a negative. Do I have that yet? I got my acceleration, but do I have a position?
No.
I've got a sign of a position. Also, I've got angular here and I've got linear here, and I need to somehow bring them together. So first off, let's bring the linear and turn it back into the angular bit. So what's the relationship between angular and linear quantities? For example, speed and angular speed. What's the relationship between the two? Let's do a problem then. I got an object that I'm swinging around in a circle. Some radius r. If it takes the time to go all the way around the circle is capital T, so the period time it takes for repetitive motion to happen once. What would be the speed of the object?
The amount of times the period occurred over time.
Period over time would,
Kind of same thing, ain't it?
yeah.
2 pi r over t.
Yeah, distance over time, so 2 pi r over the period, that's the speed. So again, distance divided by time. What's the formula for angular speed? What is, all right, so when you're going from linear to angular for the basic formulas, so like distance over time kind of thing, there's a direct analogy for rotational stuff as from the linear stuff. What would be the rotational analog of distance? Find something rotating.
Radians?
RPM.
Radians?
That would be the unit of, I missed what you said.
RPMs.
That ultimately would be the units of angular speed. You're practically there. What radians are the units of what?
Of a circle? Of a circle? Just
More general than that. A circle has a specified number of radians, but
rotational distance, I guess?
Say it again?
Rotational distance?
yeah.
I
I'm asking what
Angles.
angles what I was going for.
Okay.
Yeah, angle is the rotational analog, so the linear, sometimes referred to as translational. You typically see linear until you get to advanced levels, and then suddenly they go, we're not gonna call it linear anymore, let's give it a different name. And then there's rotational or angular. Whether something's called rotational or angular is more of a matter of habit. If you talked about rotational speed and angular speed interchangeably, everyone knows what you're talking about. There's absolutely no problem there. Typically, when you're talking about speed, it's angular speed, angular acceleration, angle, but rotational speed would mean the exact same thing. So if the linear quantity was distance, the rotational analog is basically changing the angle, and something's traveling through some angle. Speed would translate into angular speed. Acceleration translates into angular acceleration. Force translates into torque. Linear momentum translates into angular momentum. Finally, a non-Greek letter. Mass, the rotational analog of mass is the moment of inertia, or rotational inertia. Now, presumably you did cover it in 131, but what it's called depends upon the textbook. I will use rotational inertia and moment of inertia interchangeably. So, given the, time. What is the rotational analog of time?
Time.
Yeah. So, if I take any of the equations from 131, or from the beginning part of 131, I can easily translate it into the rotational equation. So if I have F equals ma, the rotational analog of this is, well, force becomes torque, mass becomes moment of inertia, and acceleration becomes angular acceleration. That's the rotational analog of Newton's second law. If I took delta x is equal to VIT plus 1/2 AT squared, one of the constant acceleration equations, the rotational analog would be delta theta is equal to omega IT plus 1/2 alpha t squared. You just take the original equation and you just transliterate. A becomes alpha, V becomes omega, X becomes theta.
So it's the same, it's just with different symbols.
The meaning is slightly different. I mean,
I know that they're technically different, but like the equation's the same.
yeah, because the base, ultimately because angular acceleration is just angular velocity divided by angular time, or divided by time. Whereas velocity is, acceleration is change in velocity over time. All right, so omega is the change in the angle over change in time. Just transliterating, x becomes theta, t stays t. So as this thing goes around in a circle, what angle does it go through? So if this travels in a circle, what is the change in the angle?
Like 360, that was that one?
Pardon?
360, like degrees, like that we talking about?
Yeah. So, yes, if I heard you correctly.
You said 360 degrees?
Okay, 360 degrees, except we're too cool for degrees. We do radians.
Pi.
How many radians is it around a circle?
Isn't it 2 radians?
Say it again?
Isn't it 2 radians?
Not 2 radians, you lost something in there. 2 pi radians. Yeah, don't forget the pi. So if I go around in a circle and it takes me a certain amount of time to do it, I just do 2 pi divided by how much time, and I have my angular speed. So what I have here is, well, that 2 pi over t, my angular speed, that's just sitting right there. So my linear speed is just omega times r. It's just my angular speed right here times my radius. The physical meaning of this is if we stood in a circle and we all held hands and put me in the middle of the circle, and I just start turning like this. The farther you are away from the center, the faster you have to run. Even though we're all, if we rotate all at the same rate, so that we all stay in a straight line, our angular speed would be the same because we all go through the same angle in the same amount of time. But the linear speed would be different. As r gets bigger, the farther you are from the center, the faster you go. So, we have this relationship that speed is equal to angular speed times how far you are from the center. Now let's do acceleration. But ultimately, that's what I'm trying to do here, trying to translate this into some rotational quantity because I got theta here, so I either needed to get them both in terms of the rotational stuff or both in terms of the linear. Acceleration is the change in velocity over change in time, as mentioned earlier. So angular acceleration is the change in angular velocity over change in time. Or if we're dealing with linear stuff, drop the vector symbol. So scalar acceleration is the change in speed over change in time. And scalar angular acceleration is change in angular speed over change in time. So I'm going to take my equation over there, that v equals omega r, and let's assume that there's a change. So if v is equal to omega r, well, the change in v would be equal to the change in omega times r. I am assuming that r is the same, and that if I have something rotating in a circle, it stays at the same distance from the center.